Today, we're tackling arguably the biggest question in physics. What are time and space, fundamentally?
It's the ultimate puzzle. We're diving into the quest for a unified theory of quantum gravity.
And this quest really starts from a major conflict, doesn't it, between our two best theories of the universe?
Absolutely. You've got general relativity on one side, Einstein's theory. It's brilliant for describing gravity, the large-scale structure, galaxies, the expanding universe, black hole.
Right, the cosmic stuff, and on the other side?
Quantum theory.
Yeah.
Equally brilliant, but for the microscopic world. It explains why atoms don't collapse, how particles interact, the whole subatomic zoo.
Okay, so two incredibly successful theories. Where's the conflict?
The conflict is, well, do they clash? They give fundamentally different descriptions of reality, especially under extreme conditions. Think about the Big Bang or inside a black hole.
Places where you need both gravity and quantum mechanics.
Exactly. And when you try to combine them, the math, it just breaks down. Neither theory alone gives us the complete foundation we need.
It's like they speak different languages about the same universe.
That's a good way to put it. And physicists, like Lee Smolin points out, are basically taking three main roads to try and find a common language, a unification.
Three roads. Okay, can you map those out for us?
Sure. The first road starts from quantum theory. It tries to extend quantum rules to include gravity. This path has largely led to string theory.
Okay, the quantum route leads to strings. What's the second?
The second starts from relativity. It takes Einstein's theory and tries to make it compatible with quantum principles. That's the road that gave us loop quantum gravity, or LQG.
Relativity route to loops. And the third is at the tear it all down option?
Sort of, yeah. It's a deeper philosophical re-examination. It questions the very foundations of both theories, looking for entirely new principles that might underlie everything.
That sounds profound, challenging the basics.
It really is. It forces us to rethink what we even mean by reality.
Let's start there then, with that philosophical shift. It seems to begin with a core principle for cosmology. There is nothing outside the universe.
Simple statement, radical implications. If the universe is all there is, a closed system, then everything in it has to be explained by things within it.
No appealing to external creators or conditions setting the stage from outside.
Exactly. No external framework. And that immediately clashes with older ideas, like Newton's absolute space and time.
The idea that space is just an empty box waiting and time is a clock ticking independently.
Right. If there's nothing outside, space can't be an independent thing. Thinkers like Leibniz and Mach argued space is just a network of relationships between objects. Take away the objects, and space vanishes too.
And time.
Same idea. Time isn't some universal ticker. Time is just change. It's the unfolding of processes, one relative to another. No change, no time.
So this forces a really fundamental shift from thinking about the universe as being made of static things to seeing it as a web of dynamic processes.
That's the crucial insight. You can't understand reality just by listing its contents at one instant. You need the story, the history, the causal links, how things interact and evolve.
Like understanding a person requires their life story, not just a snapshot.
Precisely. The universe is its story. It's an evolving network of events and information flow. A new physics needs to capture that dynamic, relational nature.
Okay, that philosophical groundwork is laid. But how do we test these ideas? Where's the empirical evidence?
We need extreme conditions, and the universe provides the perfect laboratory. Black holes.
Black holes as microscopes. How does it work?
Well, they probe physics at the smallest possible scales, the Planck scale. That's where gravity and quantum effects must meet. So studying black holes gives us clues about quantum gravity.
And the event horizon, the boundary of the black hole, seems key here. It introduces weird effects.
It really does. The horizon creates a hidden region. What's inside is cut off from us outside. This immediately challenges old ideas about objectivity.
How so?
Because what's true starts to depend on the observer. Someone falling into the black hole experiences reality differently than someone watching safely from afar. Yet both views are valid within their own context. Observer dependence becomes crucial.
So objectivity isn't necessarily about everyone seeing the exact same thing anymore.
Not in the classical sense, no. And it gets stranger. There's this connection between acceleration and heat, the Unruh effect.
Ah, yes, Bill Unruh's prediction. If you accelerate, you feel heat, even in empty space.
That's right. An accelerating observer, maybe someone hovering just above the black hole horizon, trying not to fall in, would perceive themselves as being bathed in thermal radiation, like a hot gas of photons.
Wow. So the vacuum isn't truly empty if you're accelerating.
It appears not. The temperature they perceive is directly proportional to their acceleration. It fundamentally links motion, gravity, and thermodynamics.
And thermodynamics brings us to entropy, information,
Yeah.
and Jacob Bekenstein's work on black holes.
Bekenstein made a huge leap. He proposed that black holes have entropy. And crucially, he figured out that this entropy, which represents the information hidden behind the horizon, is proportional to the area of the event horizon.
Wait, the area, not the volume inside. That feels wrong somehow. Information is stored in a volume, surely.
That's the intuition, yeah. But if space were perfectly smooth and continuous, any volume could hold an infinite amount of information. You could subdivide it forever. The fact that the information is limited, and limited by the surface area, is a profound clue. It strongly suggests that space itself can't be continuous.
It has to be pixelated, discrete.
Exactly. Like matter is made of atoms, maybe space is made of fundamental, indivisible units. Atoms of space, if you will. Otherwise, how could information be limited by area?
So if space is discrete, granular, why does it look so smooth to us?
Well, think about water. It looks perfectly smooth and continuous, right? But we know it's made of H2O molecules. The pixels of space, if they exist, are incredibly tiny at the Planck scale,
Yeah.
far smaller than anything we can directly probe.
Okay, this idea, information limited by area, leads somewhere specific, doesn't it? The holographic principle.
Yes, it's one of the most powerful ideas to emerge.
Oh.
The holographic principle takes Bekenstein's finding and runs with it. It proposes that the information content of any region of space is fundamentally limited by the area of its boundary.
Meaning, our 3D reality might somehow be encoded on a 2D surface, like a hologram.
In a deep mathematical sense, yes. It suggests that reality might be fundamentally about information and how it's processed on boundaries, rather than stuff existing independently in a volume. It's a radical shift in perspective.
Okay, so we've got this new picture. Space is relational, dynamic, maybe discrete, maybe holographic. How do those two main theories we mentioned earlier, loop quantum gravity and string theory, try to build on this? Let's start with LQG, the relativity route.
Loop quantum gravity really takes that philosophical principle of relationalism seriously. Its biggest strength is that it's genuinely background independent.
Meaning it doesn't assume a fixed stage, a pre-existing space-time for physics to happen on.
Precisely. It builds space-time itself from quantum principles. This aligns perfectly with the idea that space emerges from relationships, not the other way around.
And LQG gives a concrete picture of this atomic space.
It does. It describes space as being woven from loops, forming networks called spin networks. The nodes in these networks represent fundamental chunks of quantized volume.
Quantized volume. So volume can only exist in specific minimum amount.
Yes, and area too. You can't have just any volume or area. They come in discrete packets. The connections between the nodes in the spin network represent these quantized units of area. It literally pictures space-time as a granular woven fabric.
A quantum fabric of space. Okay, what about the other road, string theory?
String theory comes from the quantum side. It proposes that everything, particles, forces, are different vibrations of incredibly tiny fundamental strings. It's mathematically very elegant and powerful.
But it has issues. You mentioned background independence earlier.
That's been its main conceptual hurdle, historically. Most versions of string theory do assume a pre-existing background spacetime for the strings to vibrate in. That seems to ignore a key lesson from Einstein's relativity.
Which is that spacetime itself should be dynamic, not fixed.
Exactly. Also, the original hope was for one unique string theory. Instead, we found multiple consistent versions, the so-called string theory landscape. Which one describes our universe? It's hard to say.
So, for a while, these two camps, LQG and strings, seemed pretty separate, almost rival approaches. Has that changed?
It really has. The mutual ignorance, as Smolin called it, is definitely decreasing. There's a growing sense that they might be complementary descriptions of the same underlying reality.
Seeing the same thing from different angles?
Kind of, yeah. For instance, both theories have found ways to calculate the entropy of black holes, Bekenstein's area law, although using very different methods. And they often get compatible results.
That's compelling, both roads leading towards the same landmark.
Right. And the holographic principle we discussed, that pops up in both frameworks too, suggesting a point of convergence.
So maybe strings aren't fundamental, but emerge from the LQG loops.
That's one possibility people are exploring. Perhaps the woven fabric of LQG at a certain scale or under certain conditions looks like the vibrating strings of string theory. The hope for unification is definitely much stronger now.
Okay, stepping back a bit. If we embrace this view, observer-dependent truths, relational reality, there's still a huge question hanging there. The fine-tuning problem or the anthropic question?
Ah, yes. Why this universe? If string theory gives a landscape of possibilities, why did we end up in one with these specific laws, constants, three large spatial dimensions, laws that are just right for complexity and life to emerge?
It seems incredibly improbable, mathematically speaking,
It does. And if you rule out an external chooser setting the dials just right,
which the principle nothing outside the universe forces us to do.
then you need some kind of internal physical mechanism.
Yeah.
Maybe something like cosmological natural selection, where universes reproduce and those with life-friendly laws become more common, or maybe other principles we haven't discovered yet.
Finding that mechanism is a huge challenge, but there's optimism.
There is. Smolin was optimistic back then, predicting a basic framework for quantum gravity within years, and that the final theory would be conceptually simple enough to teach widely. That suggests confidence in finding an underlying elegance.
It's a fascinating journey. Okay, to wrap up, let's leave our listeners with a final thought, maybe connecting back to thermodynamics, which seems so central to all this.
Well, think about how we understood thermodynamics itself better through atomic theory. We learned the second law that entropy always increases isn't an absolute unbreakable rule.
Right, it's statistical. It's just overwhelmingly probable that entropy increases in a closed system. But tiny fluctuations violating it are theoretically possible, just incredibly unlikely.
Exactly. It's about what's most likely, not what's absolutely mandated. So if thermodynamics, especially black hole thermodynamics, is what pointed us towards space being discrete and maybe even holographic,
And if those thermodynamic laws are ultimately statistical, probabilistic,
then what does that imply about the fundamental laws of physics derived from them? Are the laws governing space, time, and gravity themselves also just extremely strong statistical likelihoods rather than absolute unchanging truths?
suggesting that the very fabric of reality might have a certain statistical flexibility or fragility built into it.
It's a profound question to ponder. Perhaps even the most fundamental laws are not immutable dictates, but reflections of what is overwhelmingly likely to happen in this universe of ours.